The Gauss-Laguerre quadrature is used in order to estimate a particular integral, and this time round we're interested in the following integral. We're interested in an integral going from 0 to infinity of e to the minus x times f of x dx. So we want to get this integral, and this integral is also going to involve a certain kind of polynomial. In this case, what we need is Laguerre polynomials. So the polynomials are once again defined in a recursive relationship. So the L0 of x is defined as 1. The L1 of x is defined as 1 minus x. However, the recursive relationship is rather complicated. So L with index n of x is defined as follows. So it's a fraction, and on top we have 2n minus 1 minus x times L n minus 1 of x minus n minus 1 times L n minus 2 of x. And this is all divided by n. So this is the Laguerre polynomial, and we're going to use it when we come to actually estimating this integral, because essentially the definition of the Gauss-Laguerre approximation is as follows. So the integral from 0 to infinity of e to the minus x f of x dx is taken to be approximately equal to the following sum. So we have a sum going from 1 to n of some weight at index I, like so, multiplied by f at xi. Okay, and this w is the weighting, and the weighting is actually defined as follows. So w at I is defined once again as a fraction. It's got xi on top, and on the bottom it has n plus 1 squared multiplied by the Laguerre polynomial at xi squared. So the Laguerre polynomial at n plus 1, note, of xi squared, like so. All right, so maybe we don't want to have just a polynomial where we have e to the minus x. Maybe we're interested in a more complicated integral. For example, we might be interested in an integral starting at some limit value a, going to infinity of e to the minus r times, I'm going to use y here because we're going to do a change of variables in just a moment. So we might be interested in this polynomial. So integral from a to infinity e to the minus ry f of y dy. So in this case, what we can do once again is we can do a linear change of variables. So we can say that x is actually going to be r times y minus a, in which case we can rewrite the integral. So we can say that this integral is actually going to be equal to e to the minus ra divided by r multiplied by the sum going from 1 to n of wi times f of xi divided by r plus a. So the usefulness of this is that we can evaluate certain integrals which are, well, some of them are well known. Like, for example, if you take the gamma function. So the gamma function, the gamma of some parameter alpha is defined as follows. It's defined as an integral going from 0 to infinity of e to the minus x times x to the power of alpha minus 1 dx. So this approach allows us to evaluate these kinds of integrals much faster. Now let's actually take a look at how this is done in MATLAB. Here is an illustration of the Gauss-Laguerre procedure in MATLAB, and what's happening here is fairly simple. So we're comparing the approximate values that we're getting through the Gauss-Laguerre quadrature with the supposedly true value that we get from calculating it with the gamma function that's built into MATLAB. Of course, you have to bear in mind that gamma function is by definition a numeric procedure. Therefore, MATLAB itself also has its own tolerance values for how precise it is. However, it's better than what we'll be getting because we're approximating it using polynomials. So essentially what's happening here is we're specifying certain numbers of the sets of polynomials that we're actually interested in using to evaluate this thing. So we're saying let's evaluate it with 5, 10, 15, or 20 such elements. And then what we're doing is we've predefined some value of alpha. It doesn't really matter what it is. And we're going through each of the ends and actually calculating the Gauss-Laguerre parts. So here is the function which does the Gauss-Laguerre. Essentially, what's happening here is we're getting the actual values. That's done by getting the Laguerre polynomials using the Laguerre L function and then using VPA solve, which is a numeric solver, to get the actual values. And similarly, we're getting the weights as well. So the weights follow the formula that we've outlined previously. So we simply once again reuse the Laguerre polynomial here, and we end up with sets of x values, what we had as x subscript I values in the handwritten part of this demo, and we have the sets of weights. And then what we can do after we've got these weights is we'll simply do a dot product between the weight and x to the power of alpha minus 1, and thereby we have our approximate values. So we can compare the true value to the approximate value, and you can see some of the results here. So the results are not as spectacular as with some of the other polynomial approaches in terms of the error, but we're still getting fairly reasonable values here, and you can see that the size of the error is going down as we're increasing the number, the actual value of n.